I'm Divya. Last time I took the arts and collectibles session. We'll continue with a newer section of the awards. It's called DIY and Engineering with Beegraphy. So here we'll try to understand what is the intent of this particular section of the workshop, existing references, design and logic building towards it, and then exploring the design on Beegraphy, modeling of the design. Can try exploring materials, configurator, collaboration modes, exporting 3D printing, and then the challenge. So the brief of that particular section is that we have to develop products. It could be anything that that is a unit or a assembly of smaller units, and it needs to probably have a purpose, what it has been made for. It needs to have it needs to be like fabricated, laser cut, 3D printed, any technology that can be incorporated. Um, it needs to be assembled into a final product. So examples can be a drone frame, or it can be DIY toys. It can be practical everyday products, and it should use computational design and digital fabrication through Beegraphy to achieve it. So one of the examples already provided on the website is one of the models available on the Beegraphy marketplace. It's a drone assembly. So you have the body and the arms, and it's a laser cut. It can be either 3D printed, or it could be um, used for laser cutting these parts and then assembling them together. But at the same time, we can also look at other different DIY projects like simple toys. We have the drone frame itself. Then we can have laser cut parts such as phone stands or small DIY objects uh, for our curiosities. And then we can have stands such as for screens or fixtures in the house, and as well as we can use it for mold making purposes that we could use for other fabrication technologies like pottery or making of parts through molds. So all of that can also be utilized. So what we today would try to achieve is a drone assembly. We'll try to also keep it pretty simple. So a drone basically is, I think everyone is familiar with the setup, but I'll just go through it briefly. The drone generally has a body, which is the central part. It has arms, which are on four sides or more, and then it has these propeller units, which help it rise up above the ground. And then we need some power source for giving power to the whole assembly. So we have a battery, which is at the base, and then we have a and then the drone can be used for multiple purposes. In this purpose, it is attached. A camera is attached on the top, so it would have that kind of a housing, and then it would require some
Yeah.
antenna. Yeah.
Sorry to interrupt. I guess you're sharing something, but we don't.
Oh,
Oh, okay, now something happened.
is
We
this
didn't.
visible?
We just saw the first screen, and nothing changed until now. Yeah, we were
Okay.
just on this one
Okay.
until.
Sorry. Should I go through that again? Yeah. So, is it visible now?
Yes.
Yeah,
Yeah.
it is
Yeah.
now.
Oh
Okay.
yeah, the slideshow.
Sorry. So yeah, B graphics. So it's DIY and engineering, and then overall workflow. I've already explained this, and then yeah, basic brief for the section: making a product, which can be 3D printed, laser cut, fabricated. Intent needs to be a DIY object. It could be used for any productive purpose, and then it needs to be an assembly of units, or it could be a unit itself. And then examples would be drone frame, DIY toys, practical everyday objects, and it should use computation design and digital fabrication techniques. Then one of the examples provided on the website itself is this drone frame. It can be 3D printed, or it could be laser cut as well. But there are other examples as well, like toys, drone frames, and then we could have phone stands, small laser cut objects, some stands for uh, tablets or any fixtures that could be utilized in the house. And then we can use it for molds and molds for construction, to be used for other fabrication technologies like pottery or lost wax casting or something like that. So then what today we'll be exploring is a drone setup. I'll take everyone again through the parts. So everyone is familiar with the object. It has a body in the middle, and it has arms or four corners. And these arms are then attached to a propeller unit. The propeller's function is to raise it up by rotating. So it requires a power source. The power source is provided by a battery. Most drones have camera units, but they could be used. They could add additional functions to the drones. So in this, we can see there's a camera unit, and we have an antenna which would link to the control unit in our hands. So that's the general assembly. Today, what we can try is making the body of it, because most of the other elements could be assembled, or sorry, most of the other body elements um, could be researched and procured from the market and then attached to the body. So general DIY process is quite linear, but then it goes into a feedback loop after a while. We have an intent. The intent is translated into research. So research could be about how drones work themselves, how the configuration of each of the wings happen, how do the wings get controlled individually if the drone has to move from one side to the other. So once we have that research in our head, then we can go towards procuring systems and parts. So then we'll divide the drone into smaller systems and parts, and then we'll go ahead looking for those parts in the market. So most parts, such as the chip that programs the whole thing, or the battery, or the propeller unit, or the motors of the propeller unit, all of them could be procured in the market. And then after that research is done, it can help us in modeling, because each of these units come with each of these would come with certain connector dimensions. So this one has screws, and this could be attached through screws or nuts. So we need to understand what the sizes of those are. So once market research is done, it can help us in modeling. And once we have modeled, we can then start fabricating. Now, after fabricating, we go back into a feedback loop where we go back. If we face some issues, we go back to the fabrication, or we go back to the modeling, and then that loop continues until we have a refined product that is tested. So yeah, that's the general DIY workflow. Market research can easily be done online. You can find various websites which give you parts on a very some of them can be very cheap to acquire, so we don't have to invest our time and money into modeling them or 3D printing them. And then we also have to look for these connector parts, which could be very useful because we already know what is feasible, and then we'll make connections accordingly. So today we'll try to attempt the drone body. And as you can see, there's a central body and there are 4 arms on each corner. So I'll take us to the whiteboard. Is the whiteboard visible?
Yes.
Yeah, okay.
That's it.
Okay, so I'll start. So we need to break this form down into parts that we can then fabricate. So the first part that I see when I see this geometry is that we require um, a squarish body, which is the center part, and then we require arms coming out of the squarish body on either corners, on all the corners. And then we can use operations such as solid union to join them all together so that they become a single body part. As we see here, I think we can start with that. And then once we have this kind of a curve developed on the base, then we can extrude that particular curve in the z direction to generate the body. And then we can understand how we can go about making the housing for the chip and the battery. So I'll go to my Beegraphy thing, Beegraphy page. I'll enter into my modeling space. So I've already made a model. People who are starting out can create a new model here. You can name it as you wish. And then if you want to collaborate with people, then you can share that particular file, and you can write in that person's name and what kind of access you want to give them. So this could be very helpful for collaborative projects. I'll go into the space. I already have a script in place, but I'll start afresh. Just a second. I think it. Yeah. So let's start with making the body first. So for the body, we'll start with a rectangle or a square. So I'll just use the rectangle tool, but I'll use the center one because I wanted to start from the building it from the center, which is the origin point on the grid. The size of it, I would want it to be, so once we have done a market research, we know that the battery comes in a particular, sorry, the chip of the drone comes in a particular size. We can, for now, say it is around 40 millimeters by 40 millimeters or 4 centimeters approximately. So I'll write 40, and that would be, I'll just go with a range input so that we can use it for the configurator mode. I'll write chip housing. So chip housing dimension, and this will go into this and this. Now, this is the size we require for the chipset, and we'll then make a frame out of it, which is slightly larger than this. So we have made a rectangle. We can try making another rectangle, which is slightly larger. So here I would try to make it parametric. So say I want the frame width to be around 10 millimeters or 1 centimeter. So I'll use a range input. I can rename it to, um, or we can just say body frame. And then what I will do is I will add this frame to the chip housing to generate a slightly larger rectangle. So basically I have an inner one, and then I want some distance of that housing from the edge of the body so that we have some stiffness in those areas. So this is where the chip will house, and this is the frame of it. Now we want to develop the parts where the arms will attach. So these parts where the arms will go and attach the body. So for that, I will first, so this particular geometry has been generated from the origin point, which is in the middle here. Now, for making something in the in a rotated plane, we would require this origin point or that plane to be rotated. We want it at the corners, and a square's corners are at 45. So we'll just rotate the plane. So I'll use rotate plane. And the plane we want to rotate is the origin, which is the XY. So I'll just make a XY plane. I can put that in all the rectangles. It would give the same output. So as you can see, the plane has rotated, and the plane can then give us these directions, which are going towards the corners. How do we get those directions? Is we can deconstruct the plane. And what deconstruction means is that it can break down the plane, and it can give us the origin point, the x, y, and z vectors of those planes. So that could be very useful when we are making things in that diagonal arm. So let's make those attachment paths. So I'll just go again, type for rectangle. I'll go with a simple rectangle. The origin point would be the new point here. Sorry, it will be the plane. So that the rectangle is being constructed at an angle to the other to the existing body, and then we can give it a length and a width so that it goes outside the body. For that, I can for the length I can go for say 50 or 5 centimeters. So this I will write as the body arm length, and then we can give it a width also. So if I click on this part and I press Alt or Option, it can duplicate it, and then I can change this to width, and I'll make this as 30. So this will go here and this will go here. Yeah. So we have a rectangle, but it is not centered at the corner. So we would have to move this rectangle towards the center. So for that, I will use move, this geometry, and then I will use vector. So the direction I would want to move it is this direction, so that we can get through the deconstructed plane. And we would also have to tell it how much it has to move by. So I'll use amplitude for that. So amplitude vector, the vector we can, which line it is? I think it might be the X direction. So I'll plug this vector in, and I'll give it an amplitude, which would be basically half my width. So my width was 30. So I'll use division, and I will divide my width by 2. Because I want to make it parametric, I won't be manually putting in the parameters every time. Oh, it was the Y direction. Yeah. So if I preview of, oh, so this has gone further. So we need to give it an opposite vector. I'll use opposite to change my positive number to negative number. And then we can see it is now in the center. Great. I think we can. So we have this particular house. We have this particular arm. Now we can rotate this arm around so that we have 4 of them attached to the body. So I'll hide this, and I will use polar array. And by default, the count is 4, and the degrees are the angle is 360 degrees. So it would by default do what we expected to do. So I won't be changing that, but we can always introduce or increase the number here. Point is a center point. Again, by default, that is the 0, 0 coordinate. So I won't have to change that. Vector and angle is it's in radians right now. That's why it's written 6. Okay. So we have the body and we have the arms. So maybe I can increase the body size a bit. I can go with say 50 so that it's slightly outside. And let's try to merge all of these shapes together. So I'll introduce a component. It's called union region. We can use this to merge multiple closed curves. So if I put all of these geometries in here, and I will put my body frame. Okay, sorry, wrong frame. Yeah, I'll put this outer frame along with my arms. I can see it has done something, but I think so our inputs are in 2 different branches, and we would want them to be in a single branch for the function to perform properly. So we would have to flatten the input first. So I'll use flatten tree for that. I can press Shift and Control to plug all the data into flatten and then send it to the input. So I'll preview of this whole previous part. So as you can see, we have a body now. Sorry, a outline of a body now. We can make it a bit smoother. I guess we can use. We had fillet in the in this, but we can also try chamfer. So I'll just use chamfer curve. I'll put in curve, and you can see it is asking for two inputs for the chamfering. So we can go with say 5 millimeters range input. I'll change the name of it to body chamfer. I'll plug this in to both of the inputs, and I'll preview of the previous part. So we have the outline of the body with us. We just need to extrude this. So if we extrude it without making it into a surface, then we will only have the outer walls. I can show you that. Extrude curve. So when I do this, I only have the outer walls. I don't have the base. But we can use capping for making it into a solid. So let's go ahead with this only. I will just copy the previous slider. I will change this to body height, and I'll plug this in. Oh, it needs to be a vector, sorry. So we'll introduce a Z vector, plug in there and put that here. So we have, and we can increase this to say, can go with 40. Oh, this doesn't go all the way there. So we can increase the maximum it can go to. I'll put in 50, and then I can change it to 40. Yeah. So I have some frame. Maybe we can go with 30. Yeah. So we have the body ready. We can use cap tool to convert the open polysurface into a closed polysurface. Cap just closes all the planar cutouts. And yeah, we have the body ready. Preview off. Now, okay, so we have something closer to what we have here, but then you can see there are parts which are subtracted from this geometry. So the first part is we require a housing for the chip on the top, and then we require a housing for the battery on the bottom. So we can start with, I think, the chip first. So we require, again, we'll go with solid operations. So we are required to make a rectangle above here, and then we'll subtract the rectangle from the body. So if I go back, I already have that rectangle ready. It's on the base. Now I would like to move this up to this part because I want to subtract it from the top. So I'll use move. And then I will give it a direction, which is Z. And we already have a height for the body. So I'll just move this component ahead. We already have a height for the body, which was this one. So, and it already has a Z vector, so we might not even require it to be given. So our rectangle has moved up. Maybe we can give it a fillet so that it's a bit smoother. Fillet geometry. I'll put this in, and then I can give it a radius. So I can give it, say, 5. I'll go with a range only. So this would be chip housing fillet. I'll put this here, and I'll preview of the previous one. So as you can see, we have a outline for the housing. Now we would want to develop a solid here, and then subtract it from the base. So for that, I will extrude this geometry down. The first thing I'll do is I'll convert this curve into a surface. So for that, we can just write curve to surface, and it will convert our curve into a surface. And then we will extrude the surface so that we already have a solid right away. it has to be extruded in the opposite direction. So we'll give it a z vector, and then we will give it an opposite. And then we will give it a depth. So this would be chip housing depth, and I'll put this in here. So if I click on this, might not be visible. I can preview this off for now. Yeah, so we have an object which is going down, extruding down. And now we'll subtract this this object from the other object to get the difference. So I'll use solid. I think I'll just write difference, and we have solid difference. So solid difference, what we'll do is we will give it this first and then this. 0 level, 0 level. Maybe I'll try to swap these two and then preview off. Yeah, so we have a cavity there. I hope it is visible. The color is a bit dark. But yeah, there's a cavity, and then we can always increase the depth of the housing if we are required to, or decrease the depth. So that is where our chip will be stored. Okay, great. So now we can move on to the next part, which is the housing for the battery at the base. So now the battery also comes in multiple sizes. Its height could range. It could be two batteries together, or it could be a bunch of multiple batteries together, because the propeller can be a bit power hungry. So how do we make it? We'll again just use another rectangle at the base. So I'll go back to the origin point. I'll make a new rectangle. I'll make a new rectangle from the center. So this one, and I'll use the same plane, but I'll give different widths to it, because as we can see, it's more rectangular, so that it probably goes like that. So it's a bit more rectangular and long, probably because it's like phone battery, so it's a bit rectangular. So we can go with, say, 30 range input. This would be our battery width. Battery housing width. And then I'll copy this down and I'll change this to housing length. This goes here, that goes there. I can then increase this to, say, 60, probably more, 100, so that it goes slightly outside of our drone body, so that I can subtract and have a cavity here. So for yeah, so I think this would work. And then what we can do is we can just extrude, or maybe we can just first make it into a surface. So curve to surface, and then we can extrude extrude this curve. Yeah, we can extrude this curve. Extrude the surface. Extrude the surface, and we can give it a height. We want it in the z direction, and then we can go with, say, it's 10 right now. We can keep it 10 only. So 10 range input, and we can change it to battery housing height. I'll put this in here. Great. So now we have that. And then if I take this forward, we can then Boolean. So again, Boolean difference. Solve just like difference. So solid difference, and then it looked like this one would go into this, and this one would go into this. And then I'll just preview of I think it did the opposite. So I'll just use this and this. Okay, maybe I'll just move the plane a bit lower. Say by 1 millimeter. Hmm. Would you guys know why this might be the case?
Try reloading the script once.
Okay. It was working previously.
Yeah, there might be some backend issue at the moment, so maybe we can just proceed, and because the concept is
Okay.
What is the problem?
It's just that there's two objects that I want to subtract, like solid difference,
Mm-hmm.
and it's unable to do that. If I increase the height, would that affect? Like it's doing the other way.
Seems to be intersecting at least, I think.
Yeah, it is, but for some reason it's not.
Are there two geometries over there? Like
Maybe I'll.
blue and green?
Yeah, there are two geometries, blue and green.
Okay.
Seems to be not.
Can you turn
Maybe
off
I'll.
the one for a second?
Which one?
The blue geometry which is there. Can you turn it off and just try the intersection with green and the magenta one?
It's still not happening.
Yeah, interesting.
I'll look
Okay.
into it.
Okay. Anyway, we'll have that base. I'll show it. There's a script already ready on the back. I'll probably show it later. Maybe we can move on to generating the arms. These ones. So let's go ahead. I'll go back to the whiteboard. So we have a base frame, and then we have the arms that go out. And then we would require some units to be attached to these arms on which the propellers would be resting or housed. So what we would want to do is develop those. So for that, I'll again use the origin point and I'll move it in the direction of the arm. So we'll try to develop one of the arms and then we will polar array it on the other sides. So I'll go back to the origin point. I'll use move, and then I will use the deconstructed plane because that was the rotated plane to give it a direction. I'll use amplitude. The vector could be x, and I'll move, and we have to move it, say, we can go with, say, 100 as our length of the arm. So I'll change it to arm length. And we can see it has moved. Oh, geometry, we have not provided it yet. So it will be, it could be this origin also. So origin. Yeah. So that is how far the arm will go. So we'll be making a triangular arm here. I'll move this a bit down. So the next thing we want is to make a triangular arm. We want these endpoints as well. So for that, maybe I can move this point again, but till this part. So for that, I will again just copy the same script by pressing Alt, but instead of giving it a manual direction, I can just give it the length of the arm that we have already made. So that would be body arm length, so 50. So I'll use this, and I'll plug this in at length. So as you can see, we have a point there now. So now what we would want to do is we would want this point to go till the end on either side. So maybe we can just move this geometry again. But right now we won't move it in the, we would move it in the Y direction because we were taking X right now. So I'll use amplitude again and plug this in here. And this time we will use 30, which was here, I think half of that because we have to move on either directions. So that would be our length, and the vector would be, we were using X, so this time it will be Y. Yeah, so we can see it has moved in that direction. And we can do this again through opposite. So I'll just copy this and this, put the vector in, and then I can just use opposite. For the we can also, if we double click on a wire, we can convert it into a node that could then be used for connecting into other objects. So I'll put this in. So this could be very helpful if our inputs are a bit far away. So yeah, so we have these 2 points now, and then we have the point which we had on the other side. So now we can just use polyline tool to interpolate through them. I'll again use flatten tree just to be safe. Put the geometry here, put this one as well, and then put it in part. So Boolean, so polyline would ask you a Boolean component, which is either true or false, whether you want to make it into a closed polyline or not. So if I write Boolean, maybe I can write true. Yeah. So yeah, Boolean, and then we can change it to true or false by click on the button. And I'll just plug this in. We want it to be closed, so you can see that it has closed it now. Maybe we'll add a chamfer to this as well. So I'll chamfer the curve. And we'll use the same chamfer as we had previously. So I'll put take this down. And I'll again double click on the wire to give me a node. And then I'll put this in here. Yeah, I'll hide the previous part. So we can see we have an arm now. Now what we want to do is give it a depth, give it a frame width as well as a depth. So we can just offset it. I'll write offset curve, put the curve in. We want it to offset in the negative direction, so opposite. And right now it's 2, or we can continue with 2. So I'll use a range input for this. Can write it to be arm width. No, so arm thickness, I think. Arm thickness, I'll put this in distance. So you can see it has gone in now. And then we can loft between these two. I'll use Latin again. And then put it in curve. So you can see it has made into a loft. And then I can extrude it. Or maybe I'll move it first. So I'll move this geometry because I want this frame to be triangular. I want this frame to be like this, slightly inclined at the bottom. So I'll just move this up to this height, and we already have that height at the back. If I go to body height, so this is that, and we already have a Z vector for this. So I'll just plug this in to my vector. Yeah, so we have this component there. Now we can extrude it downwards. So I'll use extrude curve, extrude surface. And then I'll give it a negative Z value. So Z opposite just go into vector, and then I'll give it, I guess, the same value as the thickness we were giving here. But it already has an opposite, so I'll just use the same. Yeah. So we have the upper part ready. Now we need to connect it like that. Maybe I can increase the arm's length a bit more. It's very squished right now. So it's at 100 right now. I can increase it to, say, 300 and increase this to 120. Yeah, 120 seems fine. Maybe 125. Yeah. Okay. So we'll move on to the next part, which is making the inclined base. Also increase the thickness a bit more. Yeah. So I'll preview of previous part. Now for making that base, I would first need to move this point up and then again make a polyline. So that point was this one. I'll use a Z vector. I'll to move this. So move, put the geometry into move and then vector, and then I can give it. So this was moving. We already have that, the height of the body. So I'll just use the same vector, which was this one, or extrude surface. Sorry, not this one. I think this one. Yeah. So now we have raised that point to that point, and then now we can connect all of these points together. So I'll just move it a bit back and make a new polyline. I will use merge list. So maybe just flatten tree. So I'll put this in first, and then I'll put this one and this one as well. And then I'll put this into Boolean. And then I would have to again put this in so that it makes a polyline, a closed polyline. So we have this also ready. Now we can use again chamfer for this. So I'll push this down, use the same settings as the previous chamfer, and hide the previous parts and preview this on. So we can see it is also chamfered. Now we have that. Now we want to give it a thickness. So I'll again use the same settings we used previously. I'll first offset this. So offset curve. It has by default gone outside. So we will use the same settings again, which we used here. In distance, it has gone in now. Now we will use loft. So I'll just copy these two. Copy these two again down. Put the curve, the first curve, and then the second curve, and then we can preview this on. So we can see it has already lofted. Now the thing that we want to do is like extrude this. So I'll use extrude, extrude surface. We wanted to extrude in the Z direction only. So we can just use the same settings again that we have used previously. Oh, but this one is going down. So maybe we wanted to be going in the other direction. So I'll just use opposite, and would have to provide another Z unit, and I'll make a node on this vector. Put this in here, put this in here, put this in here. Yeah. So now we have now we have this part of the body ready. We can boolean this together. This could be made neater. There are many ways to do this, but currently we'll just ignore it for the time. Now let's try to make a attachment where the propeller will be sitting on. So we can just have a regular semicircle there. So for that, I'll just go with, we already have a point which we moved to that position, which was this one. We can just use this point for making a cylinder, or we can just use it for making a circle. So I'll just go with circle, origin. We can give it a radius. I'll just go with 5. I have to make this into a range input, and I'll change this to propeller connection radius. It looks pretty small, so we might have to increase that a bit. So there'll be 2 of them, one where it will be housed and the other one would be the larger, for giving it some thickness. So this one I can increase to say 10, and the middle one I can just go with a small one, say 2 or 3. 10 is also a bit large, maybe 8. And then I can loft these two together. Loft surface. I put this and this in. You can see I already have a surface. I can extrude this. Extrude surface. And I can give it a height. So that could be called, this could be radius 2. And then we will copy this range input and put it in the vector. We need to give it a vector, so that'll be the Z direction. This will go in there, and then we can call this connector height. Yeah, so we can see it has raised it up. Maybe we can go a bit more, say 5. And then it's going above our unit. Maybe we want it to be lowered, so we can just move it down again. So I'll use, and then I'll give it a vector, and then I'll just maybe push it down by half of the height. So division, this, and then divided by 2. Put the okay, sorry. So we have to give it an opposite direction as well. So the division goes into opposite, that goes into the vector. And I'll preview of the previous part. Maybe it can be a bit more thicker, so I can increase the height. 7, no, I think 6 is fine. And maybe we can increase the depth of these a bit more. They look quite flimsy. Thickness, so we can probably increase it to 5. Yeah, maybe 4. Great. So now we have these at least the arms basic parts ready. Now we would want to do is have a connector which joins the arm to the body itself. So first what I can do is I can probably boolean all of these together. So I'll use solid union. Solid union. I'll first put this geometry in, then I can, maybe I'll just flatten all of these together. So flatten the tree, put this in first, put this in, and then put the top one as well, and then put this in into solid thing. It can take some time. Now I think it's done. I'll just hide the previous part. You can see it has been joined into a single object. Now we just want to develop a connector point which connects it to this body. So for that, I can use, okay, let me hide this for some time. I can just go with, so if I'm drawing in a plan, so if I have this arm which is sticking out of that body, I have the connector part which is taking a triangular shape and has a round hair. I can just use a connector which is going inside, but this won't help it stay. So I would have to give it some object that stops its rotation in multiple positions. So I can just make a cylinder there. So a rectangle and a cylinder would do the job to help us connect it. So I'll try to develop that at this point, going inside. So we had that point, I think, I can just click this. Yeah. So we had that point here. We will just make a rectangle again from the center. Rectangle by the center. Plug this in here. But you can see it is pointed in the world's origin point, but we want it in the other direction. So I will use this particular plane, which we rotated as the plane for the rectangle. Just a second. Or maybe we can just, there is the point, yeah. What we can do is we can just make an XY plane again at that point, and then we can rotate this plane. By default, it will rotate to 45 degrees only, so that could become our new plane for generating the XY rotate plane. Yeah, so we have a basic rectangle ready there. We can give it a width and a length. So we can call this, we can maybe have it like 1 centimeter wide. So I'll call this connector width. And then we'll have a connector length as well. Put this in here, put this in here. Reduce this down. Oh, I think I've put this opposite, but this should be width. This would be length. Yeah. So we have the rectangle for that position. Now what we can do is we can have a circle here so that that we can use for making the connection point. So again, at this point, I'll double click to generate a node. Yeah, I'll move this point a bit back. So I'll just move the point. We have a new plane. We have a new plane, so we can deconstruct it again. Plane, so that we can get the directions, and then we can use it for moving the point a bit back. So I'll use amplitude vector. The point we would want to move is, the length would be half of the length we have here. So I'll use division by 2 of the length, and this will go into our length, and the vector would be one of these directions, so we can check which one. Yeah, it's correct. It is the X direction. Just move this up. Yeah, but we need it in the opposite direction, so we need to provide an opposite component. We'll put this here. Yeah. So we have the point in the correct direction. Now we can just make a cylinder. Or let's just make a circle. It'll be easier. So connection point, we don't want it to be too big. Maybe we can just go slightly larger than our width. So our width was 5. So we can just go with 3. Range input, connector radius. I will put this in to this. Increase it a bit more. Yeah. So now we have these two parts ready. Now we just want to extrude them up. But before that, we can just join them together. So I'll use region union for that. And I will put this in and the rectangle in as well. So if I preview of the rest of it, you can see we have a keyhole shaped connector with us. Because we are dealing with DIY objects, when 3D printers come in play, we require some tolerances. So we cannot just subtract the same shape from the body. We require some level of tolerance outside, some level of slightly offset outside, so that the object can be then fit inside. It doesn't have to be exact like fit because of the limitations of fabrication technologies. So we need to add some tolerance to it. So I'll just add that tolerance here. It could be as less as point like 1 millimeter, half a millimeter or something. So I'll just add, for exaggerating it, I can add like say 1. Range input, I'll call this connector tolerance, and I'll put this in, and then I can use that as for offsetting this curve. Distance, it looks a bit too much, so I'll just go with 0.5. I'll just make a new one. I'll plug this into distance. Yeah, so we'll use the outer one to subtract from the from our body, and then we'll use this one to attach it to our the arm. So if I extrude this now, I can make a boundary out of it first. So I'll just put this in, and then I will extrude this surface up by the same height as the body. So that was arm thickness. I've lost my own.
I guess we need to introduce node search.
Yeah. Where did I lose it? There's arm thickness. Where is our body? Oh, body's a bit up. Yeah, so there's body height here. So I'll just use this vector. Right. Yeah, so we have raised that up. Now we just need to, so we have it made in one position. We need to polar array it across. So I'll use polar array. This one, I'll put in the geometry. By default, it is using the origin points. It is coming in the correct position. And then I'll use solid difference. Solid difference. So I'll put these geometries into one, and then body is here. So I'll put this in as well. And if I hide the previous paths, I'll just take it up. Maybe I need to do it opposite. I think there is some.
So solid difference is not behaving today.
Yeah, it's not behaving today. Maybe I should flatten this. It was working previously. Yeah, there's some issue with solid difference.
Yeah, we have a bug, obviously.
Yeah, yeah.
When was the last time you tried? When it worked?
It's just today only. I made the script before and it was working. So might be some. Maybe I can try increasing the height. Where is the Z vector? There's still some issue with this.
Yeah, to bet it happens on the live workshop.
Anyway, I just okay. I'll just show the other one. It was working on that anyways. So we can just move forward. I'll just connect the body height again to I'll just connect this again to that. Yeah, so I mean, it should work ideally. It's probably just a simple bug. So this would then subtract from this so that we can get some outline here, and then we can boolean this to this as this object as well, so that we have a solid object here. So and then we can just rotate this around. So this was a prop. I'll just use polar array. Yeah, so that gives us the other arms as well. So then we can go around printing all of these individually. So for printing them, wait, what I can just do it, I'll just disable this whole script. It's basically the same thing, and I'll just preview on my previous script.
I wonder whether it works here.
Oh, it should. It is working. It has subtracted the outer shape, and it is boolean in here. It might be. I did flatten it. Solid. Oh, does it go in the same, or was I using some other solid union? Might be the case.
So it's solid difference that has an issue.
There's a solid difference also here. Yeah, there's a solid difference. Might be an issue with this particular component. Some simple bug can be probably modified. So yeah, so idea was that you just have you just boolean this connector to the arm, and you boolean difference, a slightly tolerance based cutout into the body, and then you can attach them or assemble them together. This particular one also shows us the battery housing, which would come down. And then and then what we can do is, for instance, we have this. If I want to 3D print this particular thing, I can type in STL exporter, and I'll just connect this geometry in. I can give it a name, say body, and then I can go into the DIY engineering, and I can export this one. It can the name will change once you refresh. So you can select this, and then you can export that in high quality. So I'll just try downloading it, and you can see it has downloaded. I can view it in in preview already. Pretty simple geometry. One thing I'd like to tell is that I have not currently solid difference the how the chip will attach to this. So the chip will have nut and bolts on all the four corners. So we would have to provide more cutouts there for the screws to go in, as well as we require a housing or a connection point for the camera that will come on the top. So that also needs to have like few more holes on all the four corners. So you can probably see there's some holes here for connecting the chip, and then you have additional holes on these points for connecting the camera on the top. So you require a lot of connector points for this to work. And then some of the rest of the parts can then easily be yes, then rest of the part like the propellers, etc., can be it's not switching. No, I'll just enable this whole thing again. Yeah. So I've currently modeled them, but these parts could be easily procured from outside, and then we can develop connector points based on how they connect through real life objects, and then we can just use them right away. Just a small. Yeah, so I think this object can then be taken to configurator mode. Because it's a solid difference file, it can take some time to modify, but you can see, I think these are the other scripts parameters, but all your ranges will come here, and then you can modify them in the form through this, and this could be shared with the clients so that they can modify it and then give us an output. So yeah, and then there could be other ways in which you can simulate it, but because it is using online graphics, it can be a bit laggy, but then you can try various things. So yeah, it was a very basic exercise on how to develop a drone frame. Anyone has any questions on any part of?
I like how you animated it.
Yeah, it's a bit laggy, but some parts remain.
Very interesting. No, it gives like a complete DIY functionality that anything which is not available can be modeled, and whatever is, let's say, quicker and more resource efficient to just buy, like propellers, motors, can be just bought in, and I can customize my drone as per my convenience. So wonderful.
Yeah, that feedback loop can help us a lot. So once you have fabricated something, maybe you will discover that the weight of the drone is too heavy. So you have loading factors. So if the weight is too heavy, then you would have to decrease down certain parts of it. So the material needs to be optimized. So the image that you have seen, that you see here, is topological optimization, but could be much simplified if you have just like a box, like a simple frame outside. So various methods can be used for getting that real life feedback into the model, and then Beegraphy can help us parametrically modify all of the components so that it makes our life easier and not model again and again.
Yeah.
So, yeah.
Perfect.
Great. So, should we take a break and then, yeah.
We are running behind our schedule, so maybe we can skip the break, Larnik. What do you suggest?
What if we make it like very short? Like,
yeah, sure.
I thought maybe people wanted to I don't know, go grab a glass of water or coffee.
Yeah, always a good idea.
If anyone has any questions, it's the best time to ask. Alfia, I just read your response. Yeah, I think for the competition, you would have to use external rendering tools. I didn't know about Viscom, but there are plenty of others. Maybe closer to the end of the competition, we can add that feature into Beegraphy.
That would be nice.
Divya, can I ask you to share the buggy script with me?
Yeah, sure. I'll just share this. It's interesting because it was working in the script above, but
which is in
it can be in the same script. It was in the same workspace. It was working in the script which I had made previously, but it was not. So might be some geometrical thing. Some.
Ayush had the same problem, right? But by the way, Ayush, did it work when afterwards?
Yeah.
So even Rhino has Boolean problems a lot. So if your object is just touching at a point and not completely going through another object, sometimes it won't Boolean it properly. So if two faces are just on each other, then sometimes it can cause an error in Rhino as well. They need to be through and through most of the time.
There is one issue I'm aware of is like if it's just touching the edge, then it will have a problem. Like if it's like tangent.
Yeah, that also.